Hello, class. I'm sorry to have to begin the semester this way, but I have to be in Atlanta uh, today for the day of the first class, Tuesday. My daughter has follow up with a surgeon after some fairly serious surgery. So I'm going to attempt to record the first lecture. We'll see how this goes. This is my first rodeo at this. We'll do all of the first class introductions and all on Thursday. So please attend. But your first assignment is to watch this video. Okay, so the first module of the course will be on steam system optimization, and we will spend probably a good third of the semester looking into the nuances of industrial size steam systems. So let's move on into this. Perhaps this thing wants to. There we go. Okay, so primary course divisions: introduction, steam system or steam generation efficiency, resource utilization, steam turbines, steam distribution system losses. And some of this we may skip there, but I will give you slides on all of this. Perhaps we'll discuss space heating with steam, steam sparging, steam traps, flash steam vent condensers. And those are probably more topics than we will actually get to, but we will see how it goes. Just some statistics to get started. The U.S. industry consumes about a third of the energy consumed in the United States. As you can see, more than 40% U.S. natural gas is consumed by industry. 28% of U.S. electrical demand is industrial, and energy is a key factor in promoting growth, economic growth, jobs, and promoting manufacturing in the States. You can see the pie chart. That's kind of old data, but in 2004, this data trails considerably in time. We can see industry accounted for 34% of total U.S. energy use, 28% transportation, residential 21%, and commercial 17%. This is looking at energy use in manufacturing plants by size. And what you see is that there are a whole bunch of small plants that use a fair amount of energy. Then we have mid-sized plants that are using 100,000 up to 2 million. And then we have large plants. There's about 6,802 as of this point in time. That's 1998. But you see those little over 6,800 plants use 53% of the energy. So if you want to address energy conservation and make a big impact, what this says is that you need to address the big users first. And DOE has done a lot of that in the past and continues to. This is looking down at a typical industrial facility. I don't know if there is any one facility that could be deemed typical, but anyway, this is kind of like an average snapshot of what a lot of different companies do. We see that steam and process heating account for, 73% of the overall energy use. And that's typically, fossil fuel driven, most likely natural gas. Some industries, pulp and paper, use black liquor derived from the process. Waste materials such as bark and waste wood, that sort of thing, get used, and many other things that we'll talk about. Some of those during the semester. Okay, introduction. We'll move on in to that for a little while. Okay, so this is going to be just a list of some steam system components that you, unless you have a background in this, you probably don't know a lot about, specifically about many of these things, but we will discuss them through the semester. So the boiler is going to generate the steam, boiler auxiliaries, all kinds of things, deaerator, boiler feed pumps, fans, forced draft, combustion air fans, induced draft, fans pulling exhaust gases out of the boiler, etc. Steam piping, obviously you got to distribute the steam to where you're going to use it. Water treatment equipment, water treatment very important so that we don't foul up the internal heat transfer surfaces on heat exchangers and the boiler itself. Turbines for either electrical generation or can drive pumps, fans, air compressors, that sort of thing. Heat exchangers take the energy in the steam and move it into a fluid, some sort of for a process use. Pressure reducing stations, often we will generate steam at a fairly high pressure for distribution and then let it down through pressure reducing valves and or back pressure turbines. If it's saturated steam, by controlling the pressure, we control the temperature, which is useful for constant temperature type applications. Fuel storage and handling equipment. If it's natural gas, it's pretty easy. If it's solid fuel, it's a little more difficult. Steam traps. They pass condensate on back to the condensate return piping that goes back to the boiler house, and they are supposed to close in the presence of live steam so that they don't become a steam leak in the system. And then the condensate recovery and return system, the piping and pumps, etc., that get the condensate back to the boiler house. Okay, so we're going to start with a fairly simple system here, and then we'll add components. We're showing here that we have two boilers up at the top. One could be standby. We could be using both of them. It just depends on the system. It's nice to have backup boilers. Things do break and go down, and it's good if your plant doesn't go down if you lose one or two boilers. And so we're showing the steam coming out on this line and coming down. So this is a simple system. Basically, we're operating at a single pressure. So we pass it into, this looks kind of like a cartoon of a shell and tube heat exchanger, where we would have a processed fluid coming in and being heated and going out. So the steam would condense inside the heat exchanger. The liquid would flow down into this device, which would be a steam trap. It's kind of like a little float mechanism we're showing in there. So when this fills with liquid condensate, it would open and the condensate would be passed down this line back to a condensate return tank, whereby it would be pumped into this is a deaerator. This is a device that you put some steam into, and it heats the condensate and it drives off any oxygen or non-condensable gases, and those get vented from the system. We typically will lose some steam, either leaks or sometimes you take the steam out so far you can't economically return it. So we have to add makeup water to the system. And so we would have city water most likely, or it could be well water coming in, being treated here, and then coming in mixing with the condensate, going into the deaerator, and then we would be pumping that back to the boiler up here in the feed water. We'll talk more about the operation of this particular type of boiler later on in the course. I think that covers. This is the steam line with a flow control valve that goes to the deaerator, which is, another term for that is an open feed water heater. And it's open in that it doesn't show it here, but there's a little vent on this that vents a little bit of steam and the oxygen and non-condensable gases to the atmosphere. Okay, so let's add some complexity to our system. So we picked up a few more boilers here. And you know, some operate, maybe some don't, depends on steam load. But now we have what we call a two-header system. So the high pressure steam coming out of the boilers is injected into this header. And then these are what we call back pressure turbines. This one, it's driving this blue box, which could be, probably is meant to indicate a generator. This would be a pressure reducing valve in case we need to drop more steam from the high pressure to the low pressure than we can get through our two back pressure turbines and heat exchanger. This back pressure turbine is driving a pump, pumping the fluid around someplace. And so the turbine takes the place of an electric motor. This is, again, our heat exchanger with a steam trap on it. And it's so where the condensate is coming into this tank here. This is called a flash tank. So when this condensate goes from the high pressure to the low pressure, some will jump into the vapor state, and that will flow into the low pressure header. The rest will flow into the condensate return tank. And so this is our low pressure steam header, which is receiving the exhaust steam from the two back pressure turbines. It receives the flash steam, and it potentially, if the pressure reducing valve is open, it can receive some steam from it. And then we have certain uses of low pressure steam. So we see, let's say we're coming off of the low pressure header going into another heat exchanger, which would operate at low pressure, so it would be lower temperature. And so we have another process fluid coming in cold and being heated. The condensate comes out of this heat exchanger to a trap, and then it goes to a condensate, a little collection tank, a flash tank. So, and this arrow indicates that this tank operates at atmospheric pressure. So we have a little bit of flash steam here that we are venting to atmosphere. So we're going to let that escape from the system. Then we have a pump that gets it back to our main condensate return tank. Then we have a pump that takes it over to the deaerator, where we have some low pressure steam applied to heat it, to strip off the oxygen and non-condensable gases. And we still have our makeup water coming in over here so that we can maintain full water level in the system. Okay. Hope you guys are enjoying this. You're probably asleep by now. I apologize. Okay, and so now we're going to go to an even more complex system. Now we're going to have three headers. So we have a high pressure header, high pressure steam, medium pressure header, lower pressure, and then our lowest pressure in the system, the low pressure steam. Right? And you can see we're adding complexity, and we can operate turbines. We're showing here 1, 2, 3 turbines receiving high pressure steam. This turbine is exhausting steam at the low pressure, feeding the low pressure header. Again, pressure reducing valve to pass steam from the high pressure to the medium pressure. This turbine is taking steam from high pressure. And just a second, I'm getting a phone call, so I have to stop for a second.